So, good afternoon, ladies and gentlemen. It is a great pleasure for me to welcome here Professor Vladislav Mantič from the University of Sevilla at this first lecture of the Nečas seminar of Continuum Mechanics in the winter semester. Professor Mantič is a well-known expert in mechanics of solids. He studied in Prague at the Faculty of Nuclear Sciences of the Czech Technical University, and he obtained a PhD degree also in Prague at the Institute of Computer Science of the Czech Academy of Sciences, but he has been worked for more than 30 years at the University of Sevilla, and so we are happy to have him here. He will present a lecture on stress singularities in boundary value problems with Robin and Ventcel boundary conditions application in finite element modeling. So please take the floor.
Thanks, Peter, for a nice introduction. So I will talk about the singularities in solid with some specific or special boundary condition. The lecture will be divided in three related but independent parts. First, I will talk about singularity Neumann-Robin problem for 2D Laplace equation in polar sector. Then I will talk about singularity Dirichlet-Robin problem for again 2D Laplace equation, but with power law variation of the governing parameter in the Robin boundary condition. And the last part, third part, I will talk about singularity Neumann-Ventcel problem for again 2D Laplace equation in a specific domain half plane. The main application of this work are linear elastic antiplane shear problem, but other possible applications are where the Laplace equation is relevant, is like stationary heat transfer problem, electrostatic problem. I would also like to mention that the Robin boundary condition is sometimes referred to as Fourier or Newton boundary condition. So in the first part, let's start the first part. Why we are dealing with continuous distribution of springs? Actually, Winkler published in 1867 a work where in Prague, where he proposed to consider a continuous spring distribution, where the linear elastic springs have appropriate stiffness parameter. And this approach is widely used in engineering problem because of simplicity of analytical studies for computational efficiency in numerical methods. Actually, this approach idealizes real boundary interface condition, modeling, for example, adhesively bonded joints, interfaces between reinforcement and matrix, crack bridging, elastic foundation, usually called Winkler bed of springs. There is a nice recent review of spring model by Vladislav in 2018, and some classification of different interface problems, including spring model, is no classification by Benveniste and Milov, published in 2001. Spring model is also called weak model, weak interface, or weak, imperfect interface, linear elastic interface, or Robin interface, or boundary condition, as I already mentioned. And it is widely used in the design of adhesive joints, and also studies of crack initiation and growth in adhesive layers. In general, engineers are interested in to know, to characterize stress concentration as singularities in the vicinity of singular point, typically called corners, due to discontinuity in geometry, in material, or in boundary or boundary condition. The knowledge of asymptotic solution for elastic field in such corners allows us to develop special finite element approach of special finite elements whose shape functions are enriched by this asymptotic solution, so we can achieve higher accuracy in problems including such corners with low computational costs. Especially useful is the This approach is useful for numerical solution of problems with cracks and spring type of interfaces and bridge cracks with linear bridging law, which actually we are using in solving some engineering problems. However, the problem of corner singularity with spring condition is very tricky because this condition combines in linear relation derivatives of displacement, solution of Laplace equation, and the displacement. So previous attempts to deduce asymptotic series expansion for corners with spring condition were only partially successful, providing just first terms, sometimes just first terms of asymptotic series. In fact, boundary value problem with Robin boundary condition have attracted considerable attention also in mathematical literature. I would like to mention work by Gasly, 1992, Kostabel and Dosh, 96, Quarteroni and co-workers, Serge Niquez, are also Dagmar Metkova recently. Which is the aim of this work? It basically is to develop a general analytical procedure for deducing expression for elastic field near the tip of single material corner, only one material, with Robin boundary condition on one side. I will denote Robin boundary condition by this spring distribution, and this homogeneous normal boundary condition on this side, on gamma 1. Gamma 1 homogeneous normal, and on gamma 2 homogeneous Robin boundary condition. As I already mentioned, Laplace equation is the governing equation of equilibrium for out of plane displacement U. And linear elastic is isotropic material, and this is basically corresponding to anti-plane shear problem. Our requirement for our procedure was that the procedure can be easily implemented in computer algebra software to be able to obtain automatically closed form expression, because this expression can be relatively large and complicated. So we consider this corner, this omega interior solid angle. So the Robin boundary condition is in terms of representing the material representation of spring distribution. It has this form where sigma theta theta is derivative of displacement u, and k is the stiffness parameter of this spring distribution. In this case, we consider that it is uniform along the Robin boundary path. We define, actually, the stresses are computed also in terms of the material parameter mu, which is shear modulus of this linear elastic material. Governing parameter is gamma, which relates the stiffness of springs and stiffness of the bulk material. So the boundary value problem defined, actually, we have defined just condition inside the domain, which is Laplace equation. On gamma 1 part, we have normal derivative is 0, and on this Robin part, we have this homogeneous Robin boundary condition. So we would like to know the asymptotic expansion of the solution U in the neighborhood of this corner tip. Our procedure is based on the kind of double asymptotic series, which includes main singularities or main terms, and then also to each main term we have a series of shadow singularities, shadow terms. So main terms are associated to the principal part of the boundary value problem. So we replace Robin boundary condition by the homogeneous Neumann boundary condition. And then to each we denote these main terms like uj superindex 0, and the associated shadow terms are uj with the superindex superscript k. So we expand the solution of this problem in the neighborhood of the corner tip in terms of uj terms multiplied by factors kj, which are generalized stress intensity factors, which depend on the full formulation of the boundary value problem. This is the uj, which is given in terms of the sum of the main term and the summation of associated shadow term. The main term is very easy to find. So actually is Neumann solution of the Neumann one problem. We can find it in many textbooks, and this is the, let's say, main term as a function of the singularity exponent lambda j, which has explicit expression in this in the Laplace equation. To get shadow terms, we need to define a recursive, infinite recursive system of non-homogeneous Neumann-Neumann problems. So if we have computed, for example, U0, we have k minus 1 for k equal to 1, and we can formulated the problem P1. And subsequently, we define problem P2, P3, and always in the right-hand side, we use the potential or displacement from the previous solution. In this way, we can construct the sequence of this solution. How to find the solution? We use general results for singularities analysis started by Kondratiev, 1967, Kostabel-Dosh, 93, Griswold published two textbooks. So we know that the expression can be of these terms, or this singular solution can be given in the form of a series which includes power logarithmic singularities in the polar coordinate system. So we used, in order to have already guaranteed the fulfillment of the Laplace equation, so we use complex variable. So in this way, we obtain harmonic function with some coefficient, and we have here expression lambda j are singularity exponent of main terms, and exponent k indicates the shadow term or order. We have two, let's say, expressions. We have two coefficients, a and b. Ljk is the largest power of the logarithm, is the expression of shadow term. Using the standard expression of the complex variable in terms of polar coordinate system coordinates. So we get this expression, substituting, we obtain this expression for each shadow term. Our task is to determine the coefficients a and b. So we use a boundary condition, and for each this recursive system of boundary value problems, this is the expression for the coordinate theta equal to 0 on the gamma 1. From this, we obtain the coefficient a, j, k are 0. So we have just coefficient b. Now we look for the Robin boundary condition for theta equal to omega, the gamma 2 boundary part. We obtain this equation in each of these recursive problems. Here we already know coefficient b from previous, let's say, iteration, and we compute coefficient b for the current step k. In this way, we can generate the analytically solution. We use computer algebra software, so it can be done quite automatically. In order to compute this coefficient, we still need to reorganize this term in extracting the logarithm powers of logarithms. We generate this expression of omega, and then we end up with the system, linear system for each recursive boundary value problem. This is the system with upper triangular matrix, and B are the coefficient, unknown coefficient of this shadow term, and G is given by this already known coefficient from previous iteration in this recursive system. These are the expression of the matrix M, sorry. So in some situation, when sinus of lambda j plus 3 times omega equals 0, the elements on the diagonal, these elements vanish, they are 0. So we can have a non-solvable problem. Actually, it can happen, and in this case, what we do, we increase the size of this of the power of this logarithm. We increase the size of the matrix of the system, linear system, by 1. We sum 1, so we have a larger matrix. It is again square matrix, 1 row and 1 column, one more column. The coefficients of these systems, we can find the solution of this system. We have some, let's say, non-uniqueness in the term d, j, k, 0. but it's not a problem because actually it can correspond to some higher order main term, so we can set it to 0. Just to clarify, this situation can happen when omega divided by p is a rational number. So we call it like omega like critical number. And actually it happens if it can be written in this form of the rational number, in this form of the fraction, where it's in the irreducible fraction for, okay, this is natural number, okay? For the iteration k, for the shadow terms k, this is a natural number. We arrive to this classification, to the details of deduction of this classification of asymptotic series is not so trivial, so I don't go to detail, just to clarify. So depending on the number, on the angle omega, the solid angle omega of this polar sector, we have a possibility of 3 kinds of double asymptotic series expansion. If omega divided by p is not a rational number, so we have infinite series without logarithmic terms. If this fraction is a rational number which can be written in this irreducible form, so we have just maximum number of shadow term is q, and there is no logarithmic term, so we obtain exact solution in closed form. And in the last, most complicated situation, if omega divided by p is this rational number of this form, so we have infinite number of shadow terms, and for k, this integer part of this number gives us the number of logarithmic terms, number of powers of logarithmic terms. So this is the classification, and we can compute the error in the fulfillment of the Robin boundary condition, because if we have just truncated series, in general we will not fulfill the Robin boundary condition. So just to show how does it work, imagine that we have just truncated series with 2 shadow terms, and we substitute this to the Robin boundary condition. We can compute absolute error of this Robin boundary condition in this form. Substituting here, we obtain this expression. This first term is 0. These 2 second terms together, the second and third terms give 0. Fourth and fifth also together give 0. And just the error in the fulfillment of Robin boundary condition is given in this in the form of the last shadow term we use in the truncated series, because the order of shadow terms is increasing, so it's a kind similar like we do in Taylor series. So the order of our error is increasing with the number of shadow terms included in the asymptotic expansion. Let's have a look on some examples. Excuse me. So let's start with the 90-degree corner. Imagine that we have this Neumann boundary condition. Here we have Robin boundary condition. In this case, omega divided by p is 1/2. So it is in this form of the irreducible fraction. In this case, p is equal to 0 and q is equal to 1. So we have just one shadow term, and we have exact solution for the term uj. So we have this expression for uj0 and uj1, and together we have this term of the asymptotic series in the closed form. This is the expression, some plots. This is the solution of the Laplace equation u. This is the sigma r zeta. Sigma r zeta and sigma theta zeta are actually gradient components of u multiplied by the linear elastic shear module. Basically, if you like, it's basically the gradient in polar coordinate. So these are displacement and stresses. Most relevant is this problem if we consider a half plane. So omega equal to 180, omega divided by p is 1, p is equal to 1, q is equal to 0. So we have infinite number of shadow terms, and the number of logarithmic terms, the powers of logarithmic terms, is actually the order of the shadow term. So we have the full number of power logarithmic terms. So this is actually the complete solution. For j equal 1, we have the main term in this form, which is basically the unit rigid body translation in the zeta direction. And if we consider the main term and two shadow terms, so we have this expression of the displacement in the neighborhood of this of the origin of the coordinate system. And here we have the stresses or gradients of displacement. So we see that stresses have logarithmic singularity in this point. So this is interesting because doesn't move. Okay, doesn't move. Maybe better. Okay. No, it doesn't move. It doesn't move. Okay, no. Oh, no, it works. Maybe you have to check. Okay, thanks. Okay, so we have seen this solution, and we will now slightly modify and reformulate the problem. We will consider the interface crack problem. So we consider the full plane. We have in this plane, these two half planes are bonded by this spring interface, which which models adhesive interface. And so we have and this is unbonded part, so we kind of cracked it at this point. I would like to know the solution in the neighborhood of this crack tip point. So the full problem is written here. We have Laplace equation, Robin interface condition, and this is homogeneous normal boundary condition on the negative x part of the negative part of the x-axis. By symmetry arguments, we can reformulate this problem to equivalent problem just to 1/2. We consider the top. So we have the even part and odd part. I will not go to all details. It is written here. Basically, we decompose the problem to the even part and the odd part with respect to the x-axis. This even part is leads to this problem. Basically, the homogeneous Neumann condition of the bottom of the half plane. So it's very easy. The solution are a combination, finite or infinite, of homogeneous harmonic polynomials. So this is not of interest. So we just will focus on the odd part, which leads to this Robin boundary condition with double stiffness on this part of the bottom side of the half plane, and the homogeneous Neumann condition on this part. We define the governing parameter gamma, which relates the stiffness of the springs and the shear modulus in the solid. We can take advantage that we already solved kind of dual problems when we had this Robin boundary part on the other side. So we just made this change of angle, and we can deduce the solution for this new problem associated to the crack interface crack problem, and this is the solution in displacement on potential U, and this is this expression for which we used eight shadow terms to obtain good accuracy. We are sure that this is the solution, because if we add more terms, it is the change of the solution is basically it cannot be noticed. And if we compute stresses, it means that basically the gradient of U multiplied by shear modulus, we obtain this expression where we obtain logarithmic stress singularities at the crack tip. So it is different. If somebody knows something about linear elastic fraction mechanics, where the typical singularity in displacement is the inverse square root. Here we have something different. The singularity is logarithmic. It is the weakest singularity, basically. We applied these results in the solution in the finite element code. So we are solving this antiplane shear boundary wavy problem with uniform load. Here we have this interface crack, we have this spring. In 2D view, we have this problem, and because of symmetry, we are solving by finite elements on the 1/4. We implemented specific singular crack tip element, which incorporates, which is enriched with logarithmic singularity in the displacement in the following way. We consider this quadrilateral singular element because the rest of the mesh are linear elements. So we use basically like linear elements enriched by function associated because we added the additional nodes in the middle of these two edges. And these are the expression for this shape function in the parametric space. Then what we do, which is classical and finite elements, then we collapse the node 1 and 4, the whole edge in this this edge is collapsed to one point in the real space, in the physical space x, y. In this way, we have an element which has in the radial direction logarithmic behavior of r times logarithm of r. So it leads to logarithmic singularity integration. Well, we applied this in the homemade code in MATLAB, but also in the commercial code Abacus, and these are resolved by MATLAB. So we consider this is the problem, actually a quarter part of the whole full problem. For the interface crack, we use different meshes of linear elements, except that we use in the neighborhood of the crack tip either singular elements, which I just mentioned, or standard elements. And this is the comparison, considering the structural parameter introduced by Lenzi more than 20 years ago, which relates thickness of springs, characteristic lengths, and the shear modulus of the material. In our case, LCH is the characteristic length of the material. We have taken the length of the crack. So for different delta, if delta is larger, the problem is more difficult to solve numerically. So for delta equal to 10, we have we computed the shear at the shear sigma theta theta at the crack tip. It is finite. Curiously, we could discuss it more in detail, but it is finite there, and we study the convergence of the solution to the, let's say, asymptotic value. We don't know exact solution. There is no analytic solution of this problem at the moment in literature. So this is the number of elements used or discretizing the Robin part. And we see this is the result using singular elements. And these are the result with increasing number of elements using standard elements. And we see that the convergence is substantially better with using singular elements. Similar, if delta is equal to 100, the problem is even more difficult to solve numerically. And again, we see that the solution with singular element is the convergence is fast. So we can conclude. We have included the. We have presented a general analytic procedure for computing asymptotic series of any given finite order in the Neumann-Robin-Cornell problem, and implemented the procedure in the computer algebra software. Double asymptotic series include main term and associated shadow terms. There are 3 classes of asymptotic series depending on the value of the interior angle of the corner. We studied some example. We have shown that the Robin boundary error in the Robin boundary condition is decreasing with increasing the number of shadow terms. And well, we used this information for the first implementation of a special singular tip element. Okay, this is the first part. I will talk now about the related problem, but we will consider problem again is Robin boundary condition, but with variation, with some variation of the governing parameter in the Robin boundary condition, basically stiffness of the spring distribution. So, and in this case, for some reason, we consider here Dirichlet boundary condition. It was useful for some application, which I will show at the end. And we have this spring distribution with power law variation of the stiffness of the spring. So it can be useful for some problems, like for example, for adhesive layer with varying thickness, or varying damage in the layer, or for bridge cracks with varying stiffness, or for interface crack with spring interface with varying stiffness. It is again antiplanar shear governed by Laplace equation, and we will again obtain double asymptotic series. For example, well, of course, if this the exponent alpha is negative, the stiffness goes to infinity when we approach the corner apex. So this is the formulation is very similar, just the Robin boundary condition changes, and we have the Dirichlet boundary condition. Okay, this is the Robin boundary condition. K is a reference value corresponding to R2 equal to 1, and it's useful for us to rewrite this Robin boundary condition in polar coordinate system, introducing governing parameter gamma, which relates stiffness of spring distribution and the shear modulus in the bulk. And for alpha equal larger than -1, it will be useful to consider this expression on the Robin boundary condition, and for alpha smaller than -1, we will consider this form of the useful for us of the Robin boundary condition. We will see now why. Following our previous work, which I showed previously, we proceed in a similar way. So we obtain approximation of displacement in the neighborhood of the corner apex in terms of some series expansion, where K and J are some generalized stress intensity factor, and terms Uj are given by the sum of the main terms and some series of shadow. So for alpha larger than -1, we will conveniently set up Uj of the superscript -1 equal to 0. So we can define the recursive system of boundary value problem in this way. From the previous iteration, we know the boundary condition in this non-homogeneous Neumann boundary condition. So we replace Dirichlet-Robin, the original problem, by Dirichlet-Neumann, but non-homogeneous. And well, the main term can be computed again in the closed form. Lambda j, the singularity exponent, have this form. And again, of course, Uj0 general do not verify boundary condition, but we will see that if we will add the shadow terms, we will obtain a reduction in the error in the Robin boundary condition. So the leading singularity exponent lambda 1, p divided by 2 gamma, is independent of alpha. This is quite relevant. And gamma, again, is the governing parameter k divided by mu. This is for alpha larger than -1. Reminded the alpha was the exponent in the variation of the stiffness parameter. For alpha smaller than -1, again, we define conveniently Uj superscript -1 equal to 0. But now we have Dirichlet boundary condition, non-homogeneous Dirichlet boundary condition on the gamma 2 part. So a recursive system, and UK are shadow terms in the iteration K in this recursive system of boundary value problems. We define the solution Uj0 in this form, where singularity exponent is again given in the closed form, and leading singularity again lambda 1 is pi divided by omega is again independent of alpha. Gamma is again k divided by mu. This is for alpha smaller than -1, and finally for alpha this is a mistake. It should be special case alpha equal to -1. So it should be alpha equal to -1. So for alpha equal to -1, these procedures which I showed now don't work, but we can obtain closed form solution for this case, alpha equal to -1. So this is, we can take this answer and check that the Robin boundary condition is fulfilled if lambda j is fulfilled this transcendental equation. So lambda j is in this interval. This can be solved numerically because there is no, as far as I know, no analytical closed solution for lambda j in this equation. So it's interesting now that lambda j depends on the material property gamma, which was the ratio of k divided by mu. So for a relatively compliant string, when gamma goes to 0, lambda j has this limit, and for very stiff strings, when gamma goes to infinity, lambda j has this expression. How to solve these recursive problems? Again, we use expression in the similar form. Previously we used this form, and now we need to modify this form in this way. So taking into account that we have the shadow terms k, and we have some exponent alpha in the power law variation of stiffness, we have proposed this expression, and we can solve both Dirichlet-Neumann and Dirichlet-Dirichlet problems using this expression. First, we clarify that all terms be equal to 0, solving Dirichlet boundary, homogeneous Dirichlet boundary condition for theta equal to 0, and then once we know that all b are 0, so we are just looking for a coefficient. We from the boundary condition for theta equal to omega, we are able to obtain the we are able to formulate the system to be solved. If we are solving Dirichlet-Neumann recursive procedure, we are applying Dirichlet-Neumann recursive procedure. So for theta equal omega, we have this system. Formula is complicated, but at the end, after some interchanging of the summation order, simplifying, we get up with this system where we have this is known from the previous iteration, and we can compute ajk, so the coefficient for the k order shadow term of the order k. So I will just go to reobtain this linear system, like in previous case. This is the upper triangular matrix. We know the right-hand side, we know n, so we can compute a. Can be sometimes be some, let's say, critical situation where these mu are 0, so this diagonal is 0, and the system is incompatible. In this case, we increase the size of the system, we increase the power of the logarithmic term, and we can solve the problem. And the Dirichlet recursive procedure is similar. We get this system here again. We know ajk -1. We are computing ajk, so we have this linear system where which allows us to compute coefficient ajk from the previously computed coefficient ajk -1, ajk -2, etc. And in the critical situation when this happens, again, we increase the size of the system, corresponding to increasing the power in the logarithmic term. If we compute error in the Robin boundary condition, so defining in this way, we can show that this error in the situation where we use Dirichlet-Neumann recursive procedure has this form, and we see here that if we increase the number of shadow terms, the order of the error is increasing, so it's better fulfilled close to the corner apex. And similarly for the Dirichlet recursive procedure, again, alpha now is smaller than -1, so this is negative. This is, we have signals sign minus, so at the end we are again increasing the power of the error, and so the error is improving where we are close to the corner apex. Here also we have some classification of the double asymptotic series expansions. For alphas larger than -1, we have this situation which is very similar as we had previously, but it changes because we have this exponent alpha. Previously we had exponent alpha equal to 0. Now exponent alpha can be any real number. Here alpha is larger than -1, and this is alpha smaller than -1. The situation is quite similar, and similar to the situation we considered for the uniform stiffness of in the Robin boundary condition. We don't need to make classification for alpha equal to -1 because we have closed source solution. Some application for this. This was actually our motivation. If imagine that we have a bridge crack, crack bridge with linear elastic springs with this variation of stiffness. By symmetry arguments, we can convert it to this problem for the half plane. Okay, so now this interface condition is the boundary condition, and this is what we have just started. So for alpha larger than -1, we use recursive procedure for directional Neumann corner problems, and we obtain what we see here. That for alpha larger than -1, the displacement has the behaviors like square root for any alpha larger than -1. So it leads to singular square root singularity in gradient. And this we don't like, because we would like to have a continuous stresses, continuous strength there. So if sorry, okay, yes. But if we take alpha smaller than -1, this is the singularity exponent lambda, which is an integer, for lambda 1 is equal to 1. So we have smooth behavior of displacement at the tip of this bridge crack. And this is what we need. For alpha equal to -1, we have closed for analytic solution. We already talked about this. So lambda 1 is between half and 1. So it is a weak singularity. So we have now the full picture. If alpha is larger than -1, we have square root singularity. If alpha is equal to 1, we have weak singularity, -1. If alpha is equal to -1, we have weak singularity. If alpha is smaller than -1, we have smooth solution in this place. So we have taken for omega equal to p, alpha equal to -3.5, and we obtain this finite series with without logarithmic term and only one shadow term. So we have the full solution for this exponent, and actually we used it in our finite element code. This is the solution in displacement and in stresses. So we see there is non-smooth in gradient, but we have no singularity in stresses. Okay, actually this is the behavior of stress sigma yz along the axis x. It is constant for negative x in this expression. So this is the full picture I mentioned. Here we have alpha, which is the power in the power variation of governing coefficient in the Robin boundary condition. And we see that for alpha from -1 larger than -1, it is a classical crack tip singularity. For alpha equal to -1, depending on the governing parameter, singularity changes from 1/2 to 1. And for alpha smaller than -1, we have continuous stresses at the crack tip. And this is the plot of lambda 1. Okay, it's very interesting result. And how we use it? In our procedure, I proposed for computing or predicting crack onset and propagation in solids. We do minimization of the total energy. We under some stress condition. Total energy is the stored strain energy plus dissipated energy. But we need a damage variable. So if we have a crack, for example, we would like to consider a crack, but we will need to have a damage variable there defined along the possible crack advance here. But if this damage variable can be introduced by springs, okay, activating, deactivating spring. But if we put here springs with uniform stiffness, we have a square root singularity, classical square root singularity at this fictitious crack tip. So what we did, we used varying stiffness in these crack advances, stiffness varying in this form, and we obtained that this finite element. For alpha equals 0, we have kind of singularity there. Alpha equal 1. This should be minus. Minus 0.5 is again kind of singularity. For alpha equal -1, it seems, you can see this green, it seems that is kind of stress concentration, actually the big singularity there. But for alpha equal to -1.5, it is basically uniform. Okay, so we have, this is the stress, and this is what we like. So we used it, we implemented in our commercial finite element called Abacus, and we still tested which coefficient dimensionless parameter m we should use to obtain basically very uniform variation of stress in the situation where it should be uniform. And we saw that with m equal to 1000 is already, we obtained basically uniform variation of stresses. So we use this parameter. Just one result with finite element with our code. This is the problem. Actually, this was in the L-shaped domain. Its original was concrete. It is fixed here, and with the stress applied here. So we expect that here we have a weak singularity in stresses, in the gradient of displacement, and we expect that the crack will appear there. So using our code based on minimization of the total energy with a stress condition, we predicted this is the black curve is our prediction of the crack path from initiation of the crack and then propagation, and these red curves indicate the cloud of the experimental results. So our prediction, just using parameters provided by the experiment, is very good, is excellent. And this is also agreement of our prediction in the force displacement diagram in this problem. So we used here spring distribution in our computer model. I cannot enter to detail. Spring distribution with variable stiffness along potential crack advances. Conclusion: so we were able to solve problems with Dirichlet boundary condition. Sorry, the Robin boundary condition with variable stiffness. The power of variation of stiffness. We have deduced double asymptotic series. We can compute any final number of the shadow term in this double asymptotic series for any power alpha in this stiffness variation. We have deduced a kind of classification of this double asymptotic series, and we also carried out testing of using this analytical result in finite element code in our implementation of the minimization of the total energy stress condition. In fact, we don't have this result for the plane problem, but typically, from qualitative point of view, the results for the anti-plane problem and for plane elastic problem, for anti-plane elastic problem and for elastic plane problem, usually qualitative, there is a good qualitative kind of agreement, for example, in fraction mechanics, the singularity of the same order, etc. So we expect that also deduction we have done for anti-plane problem could be followed also for plane problem. But at the moment we have not done it. Also, we basically know how to do it. We have already some results, related results. The last part of this presentation is dedicated to Gurtin-Murdoch material surface. What is it? Gurtin-Murdoch material surface was a concept proposed in 1975 by Gurtin and Murdoch to allow analysis of solids and nanoscale. So the surface stress at the nanoscale can be relevant, and they proposed a relatively simple model allowing to take into account surface stress. So we introduced this material surface with a kind of membrane attached and perfectly bonded to the solid boundary, and allows us to model relatively easily the effect of the surface stress. We will consider one example which has practical application, considering that the Gurtin-Murdoch material surface is just one segment, which could correspond to graphene platelet, for example. You know probably the material graphene, which is typically one atomic layer or several atomic layers. So it can be represented by, it is very stiff, at least in the longitudinal direction. So this Gurtin-Murdoch material surface embedded in the surrounding elastic material could well representing probably a platelet, for example, from graphene or other reinforcements. So in this case, we consider infinite plane. The boundary value problem can be formulated regarding this material surface in this form. I will don't go to detail on the mechanical arguments, how this can be deduced. Let's see the mathematical problem. We have Laplace equation in the whole plane except the segment. We have the jump of displacement across the segment in zero. And we have this kind of very special boundary condition with a second along this segment. Okay, so this is the second order tangential derivative of displacement, and this is the jump of the normal derivative of displacement. So the normal derivative of displacement on this half plane and this half plane can be different, and this is the jump. Okay, so because of this second order tangential derivative, there is this condition could be called Ventcel interface condition. Ventcel boundary condition was introduced in about 1950s. Also, Feller proposed in 1950s a similar boundary condition for this with the second order tangential derivative. Fortunately, this boundary condition can be, let's say, included suitably in the variational formulation, the weak formulation of this problem, which is then amenable to finite element implementation. So let's have a look on the behavior of the elastic solution in the neighborhood of the tip of the Gurtin-Murdoch material surface. So we are looking for the asymptotic series expansion in the we locate here polar coordinate system at the tip of the material surface. Okay, so we look for U for R going to zero. Okay, this is the boundary condition. This is the boundary value problem. We consider a Laplace equation in the whole plane, but now we look. We consider kind of microscope principle. So we look just in the neighborhood of the tip of the material surface, Gurtin-Murdoch material surface. So we can consider this material surface like semi-infinite, going up to minus infinity. Okay, and we look for the solution in the neighborhood of the material surface tip. Okay, so material surface is the located along the whole negative x-axis. So we have Laplace equation, jump of displacement is zero, and we have Ventcel boundary, Ventcel interface condition. Of course, it is useful to take into account that for the positive x, we have zero jump in displacement and zero jump in normal derivative because there is actually infinite smoothness of the solution. So we can, as we have done it previously, we again decompose the solution to the even and odd part with respect to coordinate y, and the even part is interesting. We have this Ventcel boundary condition now, which replaces Ventcel interface condition. The odd part is very simple. It's basically Laplace equation with the homogeneous Dirichlet boundary condition on the bottom side of the half plane. So it is just the linear combination of homogeneous harmonic polynomials which vanish on the x-axis. So we focus just on the even part of the solution, which is formulated in this form. We have Laplace equation in the whole half plane, in the upper half plane. We have Neumann, homogeneous Neumann boundary condition for positive x, and for negative x, we have Ventcel boundary condition. The governing parameter is the ratio of the bulk shear modulus and the shear modulus in the material surface. We call this material parameter gamma. It is defined here. Okay. So it's convenient for us to work in the polar coordinate system. So we define V like the even part of the full solution U. So we will work now with just V. We have Laplace equation, normal derivative with respect to angle theta, and Ventcel boundary condition. This is for angle P and for angle theta equal to 0. First, we will look for the solution when gamma equal to 0. We have just, let's say, homogeneous this condition. And it's easy to show that by using separation of variables, that there is a solution which is uniform, V equal to 1, for example, and power type solution in this form. This is a lambda J singularity exponent. So these are our main terms with lambda J for J equal to 1, 2, 3, etc. And for J equal to 0, it is 1. These are, let's say, our main terms. And we again generate a recursive system of boundary value problems. The solution from the previous step appear in this non-homogeneous kind of Ventcel boundary condition. This is the Neumann boundary condition. And we need to solve this recursive system. How to do it? We will solve it in the next slide. Just to mention that the expansion of V would be the first term, with V0 equal to 1, plus the other terms for J equal to 1, 2, etc. Vj0 we already know. These are these terms. So we need just to compute Vjk, defined by this recursive system of boundary value problems. So how to do it? We will use the answer we used previously, starting from following the result by Kondratiev, Kostadov, and Doge. We have these harmonic functions, and we look just for coefficient AJK. L is the power of the logarithm. So we developed and implemented a general computational procedure for evaluating all shadow terms. And I will just show results for the first shadow term. For Vj has this expression. This is the, let's say, the main term, and this is the third shadow term, and the order of the next shadow term we have here. This is the expression for the surface stress. We can see that actually surface stress has square root behavior. And if we compute bulk stresses in the neighborhood of the tip of the Gurtin-Mordov material surface, we have square root singularity for bulk stresses, okay? Now I will show a finite element solution for a problem motivated by this problem. We have, let's say, infinite plane or very large finite square. We have this Gurtin-Mordov material surface occupying this segment. Mu is the shear modulus in the bulk, and Mus is shear modulus in the material surface. We have basically uniform load here, the Neumann boundary condition, and homogeneous boundary condition, which correspond to 0 load here. And again, this problem can be solved by reduced to the half of this problem. So we have this Ventcel boundary condition here now in this part corresponding to the Gurtin-Mordov material surface. We have 0 Neumann boundary condition here, and outside actually we have also Neumann boundary condition, let's say on the outer part of the Gurtin-Mordov material surface. And these are our finite element result. We implemented a suitable weak formulation for this problem. I cannot enter to detail to this weak formulation. And we have this solution for displacement. This is the effect of this Gurtin material surface in the displacement. We can see here that we have a confirmation here of our result. Let's go back. We see here that it's not easy to see, but lambda J, I forgot to include it here. Oh, I'm sorry. we don't have it. So I just can say that maybe we are able to deduce it. Lambda 1 is 2 minus 1 is 1/2. Okay, so lambda 1 is 1/2 because I forgot to. So if lambda 1 is 1/2, so we have r to the power of 1/2 times cosinus of 1/2 theta. So if we go for theta equal to p, is cosinus of p half, which is 0. So we don't see this square root behavior of displacement along the material surface, but we see it in the bulk. And for the next exponent is lambda j equals to 3/2. Yes, but sorry, for lambda j equal to 1/2 still, we have this term. We have 1/2 plus 1 is 3/2, theta is t, and we have sinus of 3/2 of p, which is -1. So we have r to the power of 3/2 in the representation of displacement along the material surface, and r to the power 1/2 in the bulk. And this is what we see here. Okay? You can see it, that we have it's the derivative, zero derivative in the material surface. This from -1 to 1, we have material surface. Always it's zero derivative, but it's the square root behavior in the bulk. It's, let's say in this part, you can see the square root behavior here, and r to the power 3/2 behavior there, asymptotic here. If you look on the surface stress, we see that the leading term is r to the power 1/2, and we observe it perfectly here. We have r to the 1/2 square root behavior of surface stress near the end of the material surface, and this is the behavior of the bulk stresses which have square root singularity close to the material surface tip. So we can conclude this third part. We have deduced analytical procedure for computing asymptotic series for this Gurtin-Murdoch material problem, leading to Neumann-Ventcel problem in half plane, under anti-pressure loading. We implemented in computer algebra software, and we are able to compute asymptotic series for any finite number of terms. And as an example, we solved by finite elements a problem which indicates us that the asymptotic series is okay, because we obtain perfect agreement with the leading terms of the asymptotic series. Of course, this asymptotic series can be used for the enrichment of special finite boundary elements. Actually, we already did it, but I haven't included in this presentation. So I would like just to acknowledge this work to my students or co-workers, Sarah Jimenez, which first started to work in University Seville, then she worked in Sorbonne, Imperial College, and now she is also in the University of Oxford. Sofia Mogilevskaya and Svetlana Baranova from University of Minnesota, Nicolas Pina, Maria Herrera Garrido, Kartik Ambika Kumari, Marmunos Rekha Stavara from the University of Seville, and also we are grateful to some European project and Spanish project which allows us to develop this research. Thank you for your attention.